In this DSAM demo video, I will explain how to use Mplus to specify a number of basic dynamic multi-level models. And there will be a part 2 in this series where I discuss more advanced models. The example I'm using here is based on a simulated data set. There's two questions, two daily diary questions. One is how close do you feel to your partner right now? And the other one is how much tension was there in your relationship today? The data come from 200 individuals and there's 100 time points per person, but there's also a lot of missing data. So on average, 50% of the observations are missing. And this means that in this data set, we actually have between 38 and 63 observed occasions per person. The data are in long format, so it means that every row represents a different time point. And then the last column here indicates who this time point belongs to. So here, the first rows that we see here are from person 153. And then we have data here from person 167. What you should also notice here is the second last column in which we have the occasion variable or the time variable. And there you can see that there are indeed missing values or missing cases. So in this case, for person 167, the first observation is actually observed, first occasion. But then the next one that is actually observed is occasion 9. So 2 to 8 are actually missing. And then we see that occasion 10 is also missing and so on. So I'm not using missing values here or like a code for missing values, but the rows are just completely deleted from the data file. When we look at the input, we first have to specify the variable commands and we have to indicate the names of the variables as they appear in the data file. So in the order they appear in the data file. So I indicate here that the first two variables are closeness and tension. That's these two here. Then there are two variables that where you can see they vary across individuals but not within a person. So these would be between person or between level variables. So that's this one and this one. And then the fifth variable is actually time. And then the sixth variable is person. Next, I indicate which variables I want to include in my analysis. And for now, or in the model that I'm going to specify. And for now, that is only closeness and tension. So I do this with the use variables option. And actually this R or this equal sign is doing the same thing. So this means I can use the variables closeness and tension. And what I then also have to indicate is that these are multi-level data. So I have to indicate that there is a kind of clustering in the data. And the clustering is based on the variable person. So that's where I indicate here in the variable command cluster equals person. So then Mplus knows that all the cases that have the same number for person belong together. And in the analysis command, I'm going to indicate I want to do a two-level analysis. So it means that for all the variables that have both variability within and between persons, a decomposition will be used. And it can be visualized like this. So the closeness variable is split up in two parts. One is referred to as the between person part. And this is a person's mean over the repeated measures on the closeness variable. And then there is a temporal deviation from that mean, and that's what we refer to as the within person part. So that's this part. And the same decomposition is done also for the other variable tension. So that's done because we have this clustering and because we indicate we want to have a two-level model. This means that we can now specify a model at the within level using the within person components that vary over time. And we can also specify a between level model using the between person components, which you can think of in this case as the means of the people on the different variables. We are going to also make use of this lagged option. So I'm going to have lagged versions of closeness and tension. And for both I indicate I want to be lagged by 1. So that is, we have t and then t minus 1. And in this case, because it's daily diary data, it will be the observation today that we already have here. And to this we are adding the observations yesterday. Or actually, to be more precise, it's not the observations yesterday, but the within-person deviations from the means at the previous occasion. So that's what we get here. We are going to do Bayesian analysis. This is something that will be discussed in more detail in another video, so I'm skipping it for now. And the other thing that we're going to add here to the variable command is the t-interval option. So we are going to indicate that there is a variable time, and this indicates when the observations took place. And by adding this, and I'm saying I want the results for a step of 1 on this variable, because the variable indicates the number, or like the day actually in this case. It will give us the results from one day to the next if we look at lagged relationships. And it will take into account then also that certain days are actually not included, that certain observations are missing in our data file. So let's look at the within part of the model. So we look at the model command and then we look at the within part here. And I'm going to say I want to regress closeness on itself at the previous occasion, so yesterday. And I do this with the %1. And I want to also regress closeness on tension at the same day. And that's because it's closeness right now and tension this day. So there is an implicit lagged relationship there in how we measured it. So that would look like this. So we are regressing closeness on itself at the previous occasion. It's the autoregression, also referred to as inertia. And there is this cross regression from tension today to closeness today. We can write this also as a regression equation where we say closeness of individual I at occasion t, the within person deviation from a person's mean for this variable, is actually regressed on the within person component at the previous occasion, so for the same person, I, but at the previous occasion, so t minus 1. And it's also regressed on tension of person I at occasion t, and then the within person part of that. And there is also a residual part because it cannot be fully predicted, and that's indicated by this zeta. So it's the zeta for the variable for the variable closeness, and it's for person I at occasion t. That's what this little arrow over here is referring to. This is indicating there is a residual, and in the regression equation we represent this with the zeta. We can also add a model for the tension variable, where the tension variable is now the outcome variable. So we regress tension on tension at the previous occasion, so yesterday, and also tension on closeness yesterday. So that's how we add these two arrows to our plot. We can then write this also as a regression equation. So tension of individual I at occasion t, the within person part of this, is regressed on tension of individual I at t minus 1, also the within person part of this. And the same basically for the closeness. So closeness of individual I at occasion t minus 1, within person part of this. So we see this cross-lagged parameter here is actually this arrow over here. This autoregressive parameter over here is actually this arrow over here. And again, there is a residual part here, zeta te it. So it varies across persons and over time. It's specific to the tension variable and cannot be predicted from tension and closeness at the previous occasion. So it's this little arrow over here. We can look at this then also the residuals. We can indicate here that these residuals come from a multivariate normal distribution. The means for both variables are 0, so we have a vector, the mean vector contains zeros because it's residuals. And then the covariance matrix for these residuals contains the variances on the diagonal, which I indicated here with psi squared. And there is a covariance, but that's fixed to 0 because there's no two-headed arrow here between the residuals. For the between level, we have the two means that come from the decomposition. So these are the two person means. And of course, every person has their own mean, so that's why it's a variable. And all that we say here is that these means, these between person components, are correlated with each other. So that's the with statement. And that implies that what we are going to have is just the closeness variable, the between part of this. So for person I, there's no subscript t because it does not vary. It's the between person component. So it doesn't vary over time. There is a ground mean for this, and that's indicated with gamma CL. And there is a person-specific deviation from that mean, and that's this U here. So U CL0I, so it varies across individuals. And the same is true for tension. So we also have the between person component here. There is a ground mean, and then there is an individual deviation from this ground mean. And what we say with the with statement is that these two components are allowed to be correlated with each other. And if we would represent this, then what we can say is that the residuals come from a multivariate normal distribution, again with a vector of zeros for the means. And then we have a covariance matrix here. So the two variances, so it's the variance of this one, the variance of this one, it's this one over here. And then their covariance, and that's this two-headed arrow between the two. So this is a very, very basic multi-level model. It contains in total 4 regression coefficients at the within person level. So that's these 2 phi's and the 2 betas, or the one-headed arrows that we see in our path diagram. And two residual variances, and that's what we see over here, the 2 psi's. And then at the between person level, we have 2 means, 2 ground means. These are the gammas. So it's the average across all individuals of closeness and also of tension. And then we have 2 variances and a covariance. So that's in the covariance matrix for the between part. Now in total, this gives us 11 free parameters that need to be estimated in this model. We can extend this model by adding random slopes. And this is how we do it. We start by saying that the type is not only 2-level, but also random. And then I can include random slopes or also random variances if I want. We will see that later. But for now, we're going to look at the random slopes. And what I mean by random slopes is that the on statements, before we had just one on statement that was applying to everyone basically in the data set. What we are going to do now is going to say every person can have their own parameter for this on statement. And the way we do this is by including the on statement, then having this vertical bar, and then giving a name to this parameter, and that's the random parameter. So here I refer to it as phi CL. And when we look at the path diagram, what happens is that this parameter here becomes random, and that's then indicated by this black dot. So there's a different value for each person for this particular regression, this autoregressive parameter, this phi CL. That also means if we have a black circle at the within level, it means that we have to add this, or that this will be added, as an open circle, or we refer to it as a latent variable at the between level. So this random slope here, random regression parameter, is also now appearing at the between level. And we can do the same thing for the other 3 regressions in our model, so the other 3 one-headed arrows. And all of them now are random slopes or random effects, and all of them are then also appearing at the between person level as latent variables. Now when we move to the between person level, what we can do is, for instance, specify that all these random effects are correlated with each other. So what I say is that CL, TE, and then I say phi CL dash beta TE, That means if you look at the code, I first specify phi CL and then some others. And the last one I specify is beta TE. So it means if I use this dash, that all of these are included in this part. And I say that so now I have 6 variables here, or random effects. And I say that all of them are correlated with TE and then again phi CL up to beta TE. So this ensures that we get all these 2-headed arrows between every possible pair of the latent variables at the between level. So all of them can be correlated. Becomes a bit messy, this picture, but that is really one way at least to represent this particular model. When we think of this in terms of equations, when we think of the within person part, it looks very similar to what we had before, but what is different now is that all the regression parameters also have a subscript I. So they vary across individuals. That's what the subscript I indicates. Each person can have their own autoregressive parameter here or cross-regression parameter here and so on. The residual part hasn't changed, so we can still say that the residuals come from a multivariate normal distribution with a mean vector of zeros and the covariance matrix that is diagonal, which just contains the variances of the residuals, within person residuals, on the diagonal. The between person part now has changed because these individual slopes are no longer estimated at the within person level. They are now estimated, or their properties basically, are estimated at the between person level. And what we see is that for each, we already had this one before for the part of the decomposition, and this also, but now we also have these random slopes here that come from the first regression equation, and the random slopes here that come from the second regression equation. And what we are estimating for those parameters also is the ground mean. So this gamma CL1 represents the average autoregressive parameter, so averaged across individuals, of the autoregressive parameter for closeness. And this parameter here, gamma CL2, is the mean, so averaged across all individuals, of the beta CL parameter, and that's this one here, so it's the effect, or the regression coefficient, from tension to closeness. So every person has their own value, but the gammas here represent the means across individuals of these parameters, and then the u's represent the individual deviations from these means. And then what we can say for those deviations from the means, or those residuals, that they also come from a multivariate normal distribution. Again, these are residuals, so their mean vector will just contain zeros. And then we have a 6x6 covariance matrix with on the diagonal all the variances of the random effects, and the off-diagonal elements are all the covariances. These are the 2-headed arrows that we saw in the somewhat messy plot of the between person part of the model. Now this model contains, at the within level, we have 2 free parameters that need to be estimated, and that's the 2 residual variances. It's this psi here and this other psi here. So these are the residuals. They are still, or residual variances, I should say, and they are estimated at the within level. And all the other parameters are estimated at the between level, and what we have is 6 means. It's these 6 gammas. We could also refer to these as the fixed effects, at least in some of the literature it's referred to it as such. Although in some of the literature something else is meant by fixed effects, so that's why I prefer to call them means here. And then in the covariance matrix we'll have 21 unique elements. One way to compute this quickly is to say, because we have 6 rows and 6 columns, the number of unique elements will be 6 times 7 divided by 2. You can check this if you don't know this rule already, but that's an easy way to get the number of unique elements from a covariance matrix. So in total, if we add this up, we end up with 29 free parameters in this model. So basically we now have a model in which the means as well as all the slopes are random. The only thing that's not random is these residual variances that are occurring at the within level. But we can change this if we want to, because what we can do is we can actually make those residual variances random as well. Notice, by the way, that I'm including a somewhat simpler plot now for the between level. So this is just to indicate everything is allowed to be correlated with everything, rather than having all those two-headed arrows between all the possible pairs. But let's focus on the within person part. What I'm going to do is I'm going to draw in the residuals. So these are these circles that contain the zetas. So the zeta was used to indicate the residual. And these residuals have variances. That's these two-headed arrows. So we were already estimating these. We just did not include them yet in our picture. But these would be the different size at the within person level. But now we're going to make them random too. And we do this by just referring to the two variables at the within level. And this is then referring to the residual variances. That's what this means if we just use the name of those variables. And these are dependent variables, then using their names without anything else is referring to their residual variances. So it's about these two-headed arrows here. And with the vertical bar and then the name in front of it, we make these random. So again, we get black circles to indicate that they are random. And so we now have a random residual variance here for closeness and also a random residual variance for tension. Now the tricky thing that you have to figure out here is how to name these. And I'm using, as you can see, log VCL and log VTE. You could also just call them Peter and Jane if you want, or something else. The point is, the reason I'm referring to it as log is because at the between level, what will happen is the log will be taken of these quantities. And that's because we have to make sure that if we draw these random effects from a multivariate normal distribution, that they will not become negative. Because if it's a variance, it's not, you cannot have a negative variance. So by taking the log, we ensure that if we go back to the within person level, we take the exponent of it, we always get a positive number. So that's why I'm using this name, but actually the name is only correct in a way at the between person level. So this is what happens. We get the log of the residual variance at the between level. So that's referring to this black circle becomes this open circle here, and this black circle here becomes this open circle here. And these are then allowed also to be correlated with everything else. So now I include this VCL until log VTE, so it's phi CL up to log VTE. So everything in between is included in this dash, and that's also true here. So all of the random effects are allowed to be correlated now. So in this model, if we look at the within person level, we see we have the random slopes, subscript I, so these are not estimated at the within person level. And we see the variances also get a subscript I, the residual variances. So these are also not estimated at the within person level. So there's no parameters estimated at the within person level anymore. But instead everything is now estimated at the between person level. So we saw we already had the the means per person. So from the decomposition we had the random slopes, and now we also have the log of the residual variance. And this is also true then for the other variable. And then for each we estimate the ground mean across all individuals, so that's the gammas, and there's an individual deviation from this ground mean, and that's indicated with this U. And then the with statement ensures that all of these are allowed to be correlated with each other. So in this case we have a 8 by 8 covariance matrix with 8 variances on the diagonal and a whole bunch of covariances as the off-diagonal elements. So in total, in this model, we'll have 0 parameters to be estimated at the within level, and at the between level, we have 8 ground means, or 8 means for the different parameters or random effects. And then we have 36 elements in our variance covariance matrix here. So this brings the total number of free parameters for this model to 44. So this was it for the basic models. I will show in another video more stuff that we can do at the between level using structural equation modeling. And there will also be follow-up videos that explain how to relate the output that we can get from Mplus back to these different models and their parameters.